Welcome back. We're now looking at our new topic of complex numbers. So let's make a start by considering what they're about and how they came to be. So far, when we've been faced with equations such as x squared plus 1 equals 0, we've determined that there are no real solutions. How do we come to that conclusion? Well, let's have a look at the equation itself. Now, if we were to solve that, we'd think, okay, let's get our x squared by itself and then work our way to x. And to do that, we'd have to subtract 1 from both sides, and so that we end up with x squared equals negative 1. And then in order to find x, we would square root both sides, and so we have x equals plus or minus the square root of negative 1. And so we'd think to ourselves, hang on, we can't find the square root of negative 1 because we can't square any number that I know to get a negative answer. So we'd say there's no real solutions. And that's true, there are no real solutions. But if we define what we call an imaginary number, which we'll call I, such that I squared equals negative 1, then the solutions to the previous problem become workable. And so let's have a look and see how it works. X squared plus 1 equals 0. Subtracting 1 from both sides, we get x squared equals negative 1, and then x equals plus or minus negative 1, as we had before. But by our definition of I squared equals negative 1, and so we can say then that x equals plus or minus the square root of I squared. And then when we take the square root of I squared, we end up with I, and so our solution is plus or minus I. Now, can we take this a step further and look at something other than 1? Okay, so we have x squared plus a squared equals 0, where a is some real number, some positive real number. Okay, so subtracting a from squared from both sides, we end up with x squared equals negative a squared. Taking the square root of both sides, plus or minus the square root of negative a squared. Now, negative a squared we could write as a squared times negative 1. Now, we know that when we have a product inside a square root sign, then we can split that into two square roots, and so we have plus or minus a squared times I squared, and the square root of a squared becomes a, and the square root of I squared becomes I, and so our solution for x is plus or minus ai. Alright, let's have a look at that example that's given here. Using the imaginary number I, write down an expression for the square root of negative 16. Now negative 16 we can write as 16 times negative 1, and so the square root of negative 16 we can write as the square root of 16 times negative 1. Negative 1 becomes I squared, and so we have the square root of 16I squared. Take the square root of both of those parts. The square root of 16 is 4, and the square root of I squared is I. And so our solution to the square root of negative 16 is 4i. So hopefully you can start to see what's going to happen. Okay, when we've got square numbers, it's nice. Okay, we can take the square root of the perfect square that we know and then put I with it. But if it's not, like this one here, we've got the square root of negative 5. That can be written as the square root of 5 times negative 1. The negative 1 part becomes I squared. And we take the square root of both of those. But the square root of 5 is a surd. Okay, we can't find a nice rational answer for the square root of 5, so we just leave it as the square root of 5. But the square root of I squared becomes I, and so we write it as I root 5. Now, let's move on to the next page in these notes and go through them. Powers of I, okay, will produce either plus or minus I or plus or minus 1. What we mean by that is, let's square I, let's cube I, let's take I to the 4th power, 5th power and 6th power and so on, and see what we get. Okay, as we square I, we know this is the definition. Okay, I squared equals -1. Well, what if we went I cubed? Well, I cubed is the same as I squared times I. I squared we know is -1. -1 times I, then it'll be -I. Similarly, let's go through these others. I to the 4th power is the same as I squared times I squared, which is -1 times -1, which is +1. I to the 5th power is I to the 4th power times I. We know that I to the 4th power is 1, so it's 1 times I, which is I. I to the 6th power we could write as I squared times 3, to the power of 3. I squared we know is -1, -1 cubed is -1, and so you can see what's happening as we go, and it's just going to be a progression as we work through. And what we notice is that even powers of I produce plus or minus 1, odd powers of I produce plus or minus I. Okay, we've been looking at what imaginary numbers are. Okay, that's what I is. I is an imaginary number. But a complex number really is composed of a real part and an imaginary part. Okay? Commonly we use Z to represent a complex number, but if Z is being used for something else, we might use W or U. Okay? Now, Z equals A plus BI is our basic understanding of a complex number in what we call rectangular form. Okay? A is what we call the real part. B is the imaginary part. Not BI, but B. Okay? B is a real number, but it's called the imaginary part of the complex number. It may also be written as Z equals X plus YI rather than A plus BI, but it's effectively the same thing. X is our real part, Y is our imaginary part. And it's often helpful to write it like this in when we're linking it to graphing complex numbers on what we call the Argand plane, and we'll get to that. The real part A is also written as REZ. The imaginary part B is written as IM of Z. Now, scroll down. The diagram that we've got below just shows how the sets of numbers are related. Okay, because real numbers complex numbers are composed of real parts and imaginary parts, the set of complex numbers in mathematics really is bigger than the set of real numbers, because the set of real numbers is within the set of complex numbers. Okay, a real number itself is a complex number. It just has no imaginary part. Okay, and so let's see how we've got the set of integers, which are whole numbers. They form part of the set of rational numbers. Okay, rational numbers, you remember, are numbers that can be written as a fraction. The set of rational numbers then are part of the bigger set of real numbers, which are part of the bigger set of complex numbers. Okay, that's just a picture of how mathematicians define numbers, and to see how they are all related to one another and fit in. Okay, so let's progress a little further. Write the real and imaginary parts of the following complex numbers. Okay, here we have a complex number, Z, defined by -3 plus 2i. Our real part is -3, okay, because that's the part that doesn't have our imaginary number I. Okay, the 2 is our imaginary part. In this one here, Z equals -1/2i. We can see that there's no other constant there, there's no other number apart from the one that's with the I, so our real part is 0, and our imaginary part is -1/2. Alright, so as we go down a bit further, our next example here is fairly straightforward, and we've got write I to the 8 plus I to the 5th in the form A plus BI, okay, where A and B we know are real numbers. So I to the 8 be written as I squared to the power of 4. I squared is negative 1. To the power of 4 will be 1. I to the 5th power, we've worked out previously on the other page, it comes out as I. And so to add these two complex numbers here, then it turns out to be 1 plus I. And so we can write I to the 8th power plus I to the 5th power is equal to 1 plus I. Okay, next one here, simplify these two complex numbers Z and W. It's just a matter of working through similarly with what's done here. So just have a work through those and you will be able to see that that turns out to be 4 and W is negative 8. Now, let's look at this fifth example. Evaluate each of the following. RE of Z plus 6I. What it's really asking is, what is the real part of this complex number Z plus 6I? So we just look in there and we can see the real part is 7. So we can just write it as RE of 7 plus 6I is 7. Similarly, IM of 10, i.e. what is the imaginary part of this complex number? And we can see that IM of 10 is 0 because there's no I part. Okay, there's no plus some number times I. Okay, it's just our real number 10. So the imaginary part of 10 is 0. And as we progress through a little further, okay, RE of 2 plus I minus 3I. Okay, we just need to do a bit of simplifying here. The I minus 3I becomes minus 2I. And so RE of 2 minus 2I is 2. And this one here, IM of this, we just need to simplify that further. And as we do that, I squared is negative 1. Okay, and so minus I squared becomes minus negative 1. And as we work through and simplify that, it comes to 2 minus 2I over 2. And we can see that we could take a factor of 2 out, which will cancel with the 2 in the denominator, and we're left with 1 minus I. And so the imaginary part of 1 minus I is negative 1. Okay, so hopefully you're beginning to see how these imaginary numbers work. Okay, and really are fairly straightforward. You might think to yourself, why are we looking at imaginary numbers? And this idea that they're imaginary is crazy. But if we think about it, numbers themselves are a concept. And all we're doing here in working with what we call imaginary numbers is an extension of that concept. In fact, I think that the word imaginary for imaginary numbers is an unfortunate term. It's to imply that it's all just made up. But in a sense, all numbers are made up. They're a concept, okay, to deal with our known world. And we're just extending that a little bit further. It's no less imaginary in a sense than negative numbers. And so we're just extending that further, and they have a lot of applications in the world of physics and electronics, and we wouldn't have the technology we have today without imaginary numbers. So that's what that is all about. So we're just going to delve in a little bit deeper as we go, and you'll find that it's quite an enjoyable part of mathematics. So, having done that video lesson, you can work through in your textbook, the Maths Quest textbook, exercise 3A, just questions 1 to 9, and get familiar with working with complex numbers. Okay, thanks for listening.